Okay, so that's the transcription and recording started. So we are on to the next chapter on the list. Remember, we're just going through in order. No surprises, so you should all have looked at this beforehand. You should all have read it and thought about it and be here ready to ask me lots and lots of questions. So you can see it either on the OneNote module materials, the very slow OneNote module materials. So we're on to chapter 5. For CPU scheduling. So it's exactly the order it is here and also exactly the order that is on here. So we're just working through. Interestingly, today is one of the days where, depending on what book you bought, and I hope you have bought the book, or at least a version of the book, this is one of the times where different versions have different chapter numbers. So on your screen there, it talks about chapter 6. So for some versions of the book, it is chapter 6, and others it's chapter 5. The version that we are looking at is chapter 5. The information hasn't really changed, so don't worry about what the chapter number is. What we're going to do today is we're going to look at different strategies for scheduling processes. Now, we did talk a little bit about that before when we talked about processes. And you remember we looked at that diagram there. Where we talked about processes coming in, being ready to run. When they are ready to run and they get a slot for the CPU, they'll move into the running state. We might be lucky and they get enough CPU time to finish, so they'll just terminate. More likely, they will pause because they're waiting on something happening. I'm in PowerPoint here, or not, so this is Firefox. It's not doing anything. There's nothing for it to update. It's waiting for an I/O event, so it has gone into the waiting queue. Right up until the point that I moved that pointer there. It was in the waiting queue, ready for the I/O device, I/O interaction, in this case me moving the mouse pointer. When that has happened, it goes back into the ready queue, ready to run and update. Okay, so we'll go through this cycle until it finishes and it can exit. So we talked about that when we were talking about processes. What we want to talk about today is this bit here. What are the criteria for moving from ready to running? Who goes first? What should be the criteria for deciding how that should happen? So we're going to cover that today, but one of the things I want you to remember when we're covering it is that there is no answer. There are lots of strategies. There are lots of things that we want to take into account. There are things that we want to do, things that we probably want to steer clear of, but the answer, if there is such a thing, depends very much on what you want the operating system to do. And we've talked about that before. Different operating systems are created for different reasons. Some of them are consumer operating systems, some of them are server, some are embedded into other systems. And it really does depend on what the operating system is going to do as to which of the strategies you choose to implement. And in fact, later on, we'll talk about some choices that different operating systems have made for those different reasons. None of them are right, none of them are wrong. It's just what you have to do in order to try and get the best possible response for your operating system. So try and remember as we go through that none of this, when I'm talking about any of these things, the criteria, the algorithms, these are not the answer. They are some answers, some approaches, possible ways of doing things. So let's remind ourselves partly how we can get away with this, because a very basic reading of running programs on a computer is you run the program. It runs, it stops, you run another program. And early on, actually, that was exactly the way computers did run. You would run a single user, single tasking operating system. One person would do one thing at a time, and when it finished, you would start something else. So back in the early days of PCs, under DOS, you would start a word processor like WordPerfect. And that's all you could have. You would run your word processor, and then when you were finished your word processor, you would stop your word processor, and you would start your QuickBooks accounting software. And then when you were done with that and you wanted to send somebody out an invoice, you'd stop your accounting system and you go back to your word processor. So you do one thing at a time. As we've mentioned before, however, we are very slow compared to the computer. Now, for example, my computer's not doing anything. It's sitting here, waiting for me. And the reason I'm giving these big pauses and trying not to move is to make that absolutely clear. There's no input either from the mouse or the keyboard or the microphone. There's no output. There's no change to the screens. There is nothing happening. Or at least nothing that we can see. Because again, as we've pointed out before, there are hundreds of processes running in the background. Checking for mouse action, checking for networking, checking for antivirus, checking for a whole bunch of things. And that can happen because a lot of the time while we are working, we are not doing anything. In other words, our computer has a burst of CPU time, like you just saw there when I pressed the keyboard, it went into PowerPoint, it updated the slide, put that out onto the display and showed it to you. So it took a wee burst of CPU time to do that. But then it goes into an I/O burst. So it did something and then it paused. And then I'll do something else and it'll pause again, waiting for input or output. So if this cycle of CPU I/O, CPU I/O, CPU I/O, perhaps we can take advantage of that. And all this time that we're waiting for I/O, we could be doing something else. Hence the waiting part. Why just run one process at a time? Why not cycle through all the processes that we have and take advantage of the I/O wait that we have built in to all our systems? And that's what we'll be doing. We'll be cycling through all these processes. And part of the reason we can do that is also because computers are fast, particularly compared to us. Here's an example of a burst time. In other words, an average time for the CPU to do something. So me changing slide might take 2 milliseconds. And you can see that's the peak on this graph here. It's about 2 milliseconds. In other words, most things on this computer take less than 2,000th of a second to do. it can do it and then go on and do something else quite happily. An average typist will do 40 words per minute, say. And if there's 5 characters on average in a word, that's 200 characters per second. So the typist is typing 1 character every 0.005 seconds, which is roughly here, every 5 milliseconds. In other words, most of the operations that this computer is performing can be done in between an average typist pressing keys. And that's an average typist. That's not somebody like me that sort of pecks at the keyboard, or for someone who's thinking. That's for a typist who's actually sitting down and typing, maybe copying something from another bit of paper. That doesn't put in typing time. So there's lots of gaps in there where we can do something else, and that's what we're going to take advantage of. Okay, so we have all these processes. They're all ready to go. They're all set, desperate to get started, all sitting in the ready queue. Which one do we choose? That's the job of the scheduler or the scheduler. I'm still never sure. But we do need one of these things. It's like everything else in the operating system. It's a piece of software that has been created. It has an algorithm. It's chosen how it's going to do it. An operating system is just a piece of software like anything else. So we have to write a scheduler. Now, there's different ways that we can move between processes, and you see them there on 1 through 4. The other thing I'll remind you about is that anything on blue is something that you want to remember. So the first word, second word in the blue there is non-preemptive. I'll skip to the third one, preemptive, because it's easier to explain that and then say what the non-preemptive is. Oh, sorry, no, not. It's late in the week. So non-preemptive is where the process changes by itself. It changes its status itself. So 1 here, the process has realized that it's waiting on input and just said, nah, I'm done here. Just put me to sleep until I'm ready to go. Or I'm done altogether. Time to go, exit, quit. So that's non-preemptive. Preemptive, on the other hand, is the one that we are going to be spending most of our time looking at. That's the one where the operating system itself decides, sorry, it's time I stepped in here, and moved a process from the running to the ready state, perhaps because it's used all its time, or moves it from waiting to ready, because the operating system has detected an I/O action, has realized it's for that specific process, and knows that it can now use the CPU if it was given the opportunity. So it switches from waiting to ready. So we have preemptive, where the operating system takes charge and says this is what's happening. And we have non-preemptive, where the process itself makes a change. Preemptive is tricky. Of course it's tricky, otherwise you wouldn't be getting a course in it. Because you've got a process that's running, it's got information in the CPU, it's got access to data, it's busy doing things, and you have to store those. And we talked a wee bit about that before. That job, the specific job of saving the state of the currently running process and then loading in the new state, for the process that we're switching to, that's the job of something called the dispatcher. And we've said before that when you move from one process to the other, the fancy name for that is changing the context. It moves from one process to the other, brings in the register of values, brings in the PC, and jumps to that point in the program where you left off before. And that's not free. Changing the context is not free. It takes time. It takes time to save the current context, and it takes time to bring in the new context that you want. And again, we've got a fancy name for that. It's called dispatch latency. In other words, the time taken to stop one and start the next. And that's going to be a key metric for the approaches that we take. There are other metrics, other criteria that we'll use. We want to keep the CPU as busy as possible. It's an expensive piece of kit. So we want to give as much work to the CPU as we can. We don't want it sitting there idle. So we want to maximize the utilization that we can get for the CPU. Similarly, we want to get through as much work as we can. We call that throughput. So we want to complete processes, to get stuff through. I know for many of you, process completion seems a kind of odd way to look at it. I mean, I've, for example, got Teams, Firefox, Edge, and PowerPoint all running just now. And I've had them running since I turned on this morning. The process hasn't completed as such. But the way we're looking at this, it's in terms of work. So rather than thinking of it as an application that just sits there and you interact with, think of it in terms of specific outputs. You have an image and you're asking Photoshop to perform a transformation on that image. Or you've got a 3D image and you're doing a render. Anyone who's ever done those things knows it takes an appreciable amount of time. So that's the sort of work that I'm talking about. A particular item that you can say, yes, we have done this. So even though I've got Outlook running and it sits in the background, a piece of work might be creating and sending an email. In proper systems, not the tiny system that I've got here just for me, in proper big systems, a process that completes might be the sorts of things that we've spoken about before. A supermarket might reconcile all its debit transactions for that day in one process. So you want to complete that as quickly as you can, because you're waiting to do the credit transactions for MasterCard. And after that, you'll do the credit transactions for American Express and all the other things that you need to do. So there is specific work that needs to be done, and we want to get that throughput going. For some operations, but not all, we want them to finish as quickly as possible. So there are some things that you don't mind if they take a wee bit longer. If you are rendering that 3D scene, you know that it takes time, and you know that it won't happen immediately. On the other hand, if you click to open an email, you expect that to happen almost immediately. Perhaps not immediately, but almost immediately. So the turnaround time is important, how long it takes to do a particular thing. And of course, you want that to be as low as possible. Similarly, you don't want a process to be hanging around waiting to execute. You want that to be as low as possible as well. You don't want it sitting there. And you've all experienced that even on your own small systems, that you click an icon waiting for an application to start, and it doesn't. So you click it again, then eventually it catches up with itself. Even if it got into the ready queue and then had a wee burst of CPU just to even start and to give the idea that something's happening, that would be great. And that is the response time, how long it takes for a response to be produced. Not necessarily the finished output, but just a response. So we want to maximize some things and minimize others. So we're going to look at some strategies that we can use for that. So again, the same caveat. There is no best, there is a best strategy, but it's completely theoretical and we can't do it in real life. I'll talk about it shortly. So what we have to do is compromise. We can look at different strategies, try and understand how they work, and using these criteria, we can see how well these strategies fit that criteria. So we'll go through a few of those. Does anyone get any questions before I do look at a few of these? Okay. So we're going to have quite a few of these diagrams coming up. So let me just take a wee minute to explain the idea. So what you have is a set of processes identified as P with a number against them, and something called the burst time. In other words, how long that process would take to run. So you can see that processes 1, 2, and 3 are vastly different. Process 1 takes 8 times as long as processes 2 and 3. I was slowing down there because I was having an issue with turnaround time. Sorry, response time, because it wasn't doing anything for me, because I was doing something in the background there to get ready. So we've got multiple processes and we're going to do them first come, first served. So process 1 came in first. So this is time along the bottom. So starting at time 0, process 1 takes 24. And I know that you're all screaming at your screen saying 24 what, and actually it doesn't matter. Microseconds, milliseconds, seconds, days, centuries, it doesn't matter because these are about proportions. So if it helps, think of them as milliseconds, but it really doesn't matter. It's just the time period. The fancy name for that's the quantum. We're going to just look at a particular time period. So it takes 24. So process 1 comes in and executes because it's first come, first served. Whoever gets in the queue first, they get done first. So the first process gets done and that takes 24. And then the second process can get started. It starts at 24 and takes 3, so it finishes at 27. And then the third one that came in also is 3, starts at 27 and finishes at 30. Okay, so that's time. And we can see visually how long each one takes. And you can see that process 2 and process 3 have had to wait quite a time, particularly in proportion to the amount of time they take to execute. So we can work out some of our metrics now. So remember what we're doing. These are the 5 metrics. So we can work out the waiting time. The amount of time a process has been waiting in the ready queue. Now process 1 came in first. So it didn't have to wait at all. It got started immediately. So the waiting time for process 1 is 0. Processes 2 and 3 also, in essence, came in at time 0, but slightly after. So that was the order that they came in. So process 2 had to wait for process 1 to finish. So it had to wait for 24. So the waiting time for process 2 was 24. Process 3 had to wait for process 1 to finish, which took 24, and process 2 to finish, which took 3. So it took 27 for process 3 to even get started. So the average waiting time, if you add these three things up and divide them by 3, is 17. Which isn't that great considering that the time taken to actually perform this process is 3. So it took about 6 times longer to get started than it did to actually execute. If it helps, think of this as the queue in Aldi's. And I'm specifically choosing Aldi's because Aldi don't do different types of queue. You just join it, and whoever's there first, they get their stuff done. So whether you're behind someone with a full trolley, which would be process 1 here, that all has to get scanned, or whether you're waiting for somebody with a basket, which would be process 2, you're still behind them. Trot on over to Tesco and you have a different option. They'll actually look at what you have. So there'll be a queue that says baskets only, 10 items or fewer. It actually says 10 items or less, but it bugs me every time I see it's 10 items or fewer. So it looks at the processes and thinks, look, well, we could run this really long process, but actually what if we ran these 2 quick processes, got them out of the way, and then did the long process? So they all come in at the same time, but we have radically different waiting times. So process 2 still is 0. Process 3, instead of having to wait 27, only waits 3. And process 1 loses out, because instead of waiting 0, it has to wait 6. But on the other hand, it's a big long process, so it's not as hard for it. So our total waiting time is 3 for process 3, 6 for process 1 is 9. 9 divided by 3 gives you an average of 3, as opposed to 17 so far in the previous option. So simply by choosing the process that runs first, you can make a massive difference to what happens. And again, there's a term for it. It's called the Convoy Effect. And anybody who's ever been driving behind an articulated lorry and can't get past them because it's going slower will know what the Convoy Effect is. If you're a short, agile process getting stuck behind a long, slow process, then there's a problem. Okay, before I go on, does anyone have any questions either about how the diagrams work, how we're doing any of those calculations, or anything else? Okay, so we are here doing something called shortest job first. And I said earlier that I would tell you that there's an optimal way of scheduling. And shortest job first is it. If we can get the shortest jobs, put them through first, we will get our optimal scheduling. Why doesn't every operating system just use shortest job first then? No, the video hasn't frozen. I'm just waiting for an answer. Any thoughts? The answer is really simple, actually. We can't tell the future. We don't know how long the process will take. If you're running Word, and Word starts up a process to enter a new character onto your document, that's a very short process. If Word starts up another process to create the table of contents, that's quite a long process. We don't know the future. We simply can't tell how long a CPU request will take. If we could, it would be great. We would get our processes, figure out how long they would take, and just run them in order. So 4, 1, 3, 2. And that gives you the lowest possible average waiting time. What if, though? Because remember, we're not talking about a process completing, we're talking about a process burst, a CPU burst. Something that the process does and then stops, like me changing the slide. A quick burst to change the slide and then nothing for a long time. What if we could examine the process and start thinking how long the process may take or has taken? So instead of knowing how long the burst will be, why don't we look at how long the bursts have been before and use those as an indication of how long we expect the next one to be? So if a process has these specific burst times previously, is there any reason to suspect that there won't be much the same next time? So we can do that. We can record for each process how long the CPU bursts were over time. I know that some of you are sitting there looking at Greek characters and equations and silently quaking. The good news is you don't have to remember this. I've left it in there for those that do want to know. It's something called exponential averaging or exponential smoothing. What we're trying to do is get an idea of how long a process will take. So it's a lot easier showing it on a diagram. So a process starts up. We guess how long it's going to take. So our guess up here is 10. But actually what it took was 6. So if we guessed 10 and it took 6, well, let's make our next guess 8. But actually next time it only took 4. So if we guessed 8 and it took 4, let's guess 6 for the next one. And actually, we did well, because the next burst was 6. So we guessed 6, it was 6, so we guessed 6 for the next one as well. But actually the next one was down again, it was 4. So we guessed 6, it was 4, we averaged those out and we get 5. The next bust, on the other hand, is different. It's clearly starting to do some more work. The next bust was 13. We guessed 5, it actually was 13. So we'll average those out. 5 and 13 is 18, divided by 2 is 9. So our next guess is going to be 9. But actually this process and its CPU busts are holding steady. We guessed 9, it still took 13. So we'll average up again to 11, then 12. And you can see that our guesses converge towards what the actual CPU bust time is. So this fancy calculation here is calculating what our guess is for how long that CPU will take for its bust time, depending on its previous performance. If it took less before, we'll guess less before. If it takes more, we'll start guessing more. And that's what this does. It looks at the actual length of the bust, it predicts the next one, it guesses, and then tries to work it out. The question is, how much weight do you give to the actual CPU bust, previous one, your guess, and so on? And that's where we put in the technical name for this is a guess. It's a fudge factor called alpha. We just simply set it to a number, and we can fiddle with that number to get the best throughput. Often it's just set to 1/2. And what we end up with, where we have a preemptive operating system, and remember that's the one where the operating system's saying, you've had your time, we're done, time for somebody else to get a shot now. What we end up with is something called shortest remaining time first. So the process that we think will take the least amount of time gets shoved through first, so that we start ending up with something like this, where the short ones get pushed through so that we can finish them off, which helps us in our throughput. So we're trying to do our best for these criteria that we've created. If we fiddle about with alpha, we get different effects. If we set alpha as 0, we don't look at history. We just say, what was the last one? And some operating systems do that. They just say, well, what did you take last time? We're going to guess that's what you did this time. So we don't look back any further. Sorry, for alpha equals 1, we only look at the last one. For alpha is 0, the recent one doesn't count, and we just stick to our guess. This is an average. This is what we expect any burst of CPU time to take. So we can fiddle about with alpha to get something that's helpful. Anybody get any questions about that? Apart from the formula, which feel free to examine, but you don't need to know, particularly for the assessment. Okay, in that case, let's put it into an example. Here we have our familiar thing. We've got processes, we've got time, we've got a bust time, but we've added in a new column. We've added in the arrival time column. So instead of just having the process name and how long it's going to take, now remember, we only know this in hindsight. The CPU doesn't know this in advance. We just can look at this and see what happened. So we've got different arrival times, whereas before our processes all arrived at the start at 0. Now they're arriving at different times at 0, 1, 2, and 3. So let's see how that changes our approach. So process 1 arrives at time 0, and it helps if I point to your screen rather than mine. So process 1 arrives at time 0, so get started. So process 1 gets started. And then at time 1, process 2 arrives with an expected burst time of 4. Now by this point, process 1 has had one piece of time, so it's got 7 left. So if you now have two processes, process 1 and process 2, and we expect process 1 to take 7 and process 2 to take 4, our algorithm says, well, shortest remaining time is process 2. Chuck it in there. So at time 1, process 1 starts and starts running. Process 3 starts at 2. Oh, come on, computer. So this is going to be weird because I'm just bringing this over to make it easier for me to mark up. So we'll get 2, 3, 4. Okay, so process 3 arrives at 2 and process 4 arrives at 3. So at time 2, when process 3 arrives, process 2 has had one time period, so it's got 3 left. So the operating system looks at them and says process 2 has got 3 left. Process 3 has got 9 left, so shortest works, we're still doing process 2, so it continues on. And then we get to time 3 when process 4 arrives. At that point, process 2 has had another go, so it's down to 2. And when process 4 comes in at time 3, it's got 5. Process 2 has only got 2 to go, so it continues on. So process 2 continues and actually finishes. So it started at time 1 and it finishes at time 5, and then it's done. Then the operating system looks back to see what it's got left. It's got P1, it's got 7 left, it's got P3, it's got 9 left, and it's got P4, which has 5 left. There's nothing new coming in, so it's going to put them in the order in which it sees them. So it runs P4. So when P2 is finished at time 5, P4 starts, it's got 5 to do, so 5 plus 5 is 10. At that point, P4's done, and it goes back and looks at P1's got 7, P3's got 9. Okay, let's do P1. P1's got 7 to go. Starts at 10, finishes at 17. P1 finishes. And then P3 can come in starting at 17 and going to 26. Everyone happy with how that worked? Any questions about it? Other than, please never take the camera that close to your face again. That was quite frightening. Is anybody still awake? See if you are happy. On Teams, there's an option to sort of give thumbs up or claps or smiles or something. If you can at least do that for me, it lets me know that you are happy and I can move on. So are we all happy with that? One person's happy. Two people are happy. Everyone else is definitely asleep. Good to know. Oh no, got a thumbs up as well. Okay, so that's shortest remaining time first. So let's look at another way that we can go. Let's look at, instead of just choosing the time, let's decide about what the process actually is. Let's decide which one is most important. Now, this happens everywhere in computing. At one point, I implemented a new system for an organization, and they didn't have an awful lot of money, so they could only afford one printer. So it was one central printer for about 20 people, can't remember. Most of the time that was okay, but sometimes if somebody was putting out a big report or there was lots of people needing it at the end of the month, whatever, it could slow down. So people would complain, and some of the people were the people that could fire me, not to put too fine a point on it. So what I would do is I would set the printer priority to be higher for them. So in essence, anybody that could fire me got to go first in the queue, and anybody else could just fight it out. We can do the same with processes. We can set priorities for them, hopefully for less craven reasons than mine. But nonetheless, we can set a priority that says, okay, we'll do this one first, and then this one, and then this one. We already do it, so things like interrupts on a system get the highest priority. If something is interrupting the system, we go and service that interrupt. And you learned about that last year. So we set a high priority for that to ensure that we don't miss the interrupt. We can do the same for other types of processes. We can give interrupt priority. We can give process priorities so that the processes that we decide are the ones most deserving go first, and the ones that are less important go afterwards. But remember, this is a continuing system. We don't just, in the same way as we have here, have processes and that's, oh, we sort them out and then that's us all done. In a real system, other processes are continually coming in, other things are happening, other people are doing things. If the other things that are coming in are continually higher priority, then the lower priority processes will just never get executed, because all these new higher priority processes will come in and they will go first. Again, fancy name for it. In this case, it's starvation. The processes are starved of CPU time. So what we can do is show concern for the elders in our society. You get more priority the older you are. So as we might let an old person go first, So if ever you see me in the street, let me go first. We might do the same for processes. So as they've been sitting in the queue waiting, we won't just leave the priority the same, we will increment it using some sort of algorithm, whether it's number of processes that went before it or time it's been sitting there or whatever. But its priority will increase till at some point it then does get executed. So we've got another example here. And again, another new column. This time it's the priority column. So we've got 5 processes with 5 different priorities. It doesn't always happen like that. Sometimes some processes get the same priority. So you'd have to use another algorithm, which brings us on to another point. We're talking about these algorithms as though they are exclusive. Quite often, you will implement multiple algorithms in one system in order to cope with these issues. So again, using the team's response, is everyone happy with that chart and how that works? Give me smiles, claps, thumbs ups, whatever. I've got a thumbs up. Another thumbs up. The request was you look at these things before, you read them beforehand to get a good idea of what happens. And of course, you haven't done that. Because one of the things that it says in the module materials is that there's a mistake on this slide. So those of you that were happy with it, and those of you that just ignored me, clearly hadn't actually read it. Because apart from anything else, we have 5 processes and only 4 of them are represented here. Process 1 appears twice. So what I'm going to do is jump over this, and I'm going to set you an assignment on Teams, and your assignment is to create the proper Gantt chart for this. I'll put that up once we're done. So I'll expect you all to submit it by next week, and I'll go over it then if anybody's still got questions on it. So redraw this Gantt chart, but with a correct set of labels on it, using the priorities that are shown there. Okay, our next approach is something called round robin. This is the one actually that's you're possibly most used to. It's one of the ones that's most often used, particularly in a time-sharing system. In essence, each process gets a certain amount of time, a quantum, Q. And once that time's up, the next process gets a shot, and that's called preemption. The operating system preempts the process that's running and swaps in another process because it's had enough time. The question then becomes, how large or how small should that time quantum be? Fairness would dictate that the quantum would be low so that you swap processes and everybody gets a go. But some processes might execute if you give them a longer time. So a higher quantum might be more appropriate. So finding that value is important, not least because swapping, as we've already discussed, isn't free. It takes time to swap processes in and out. And if your time quantum is too low, you can actually spend more time swapping than you can executing. So as I said at the start, and I've been saying all the way through, there is no answer. These are choices. And you can get very different answers depending on the choice that you make. So here's an example where we've chosen a quantum of 4. So we're back to a couple of columns, one for process, one for burst time, and we're assuming they all come in at the same time. So again, we can work our way through this. So process 1 comes in and starts executing. Dum-de-dum-de-dum-de-dum, gets its 4, which is what our time quantum is. So after 4, the operating system says, nope, you've had enough. Now contrast this with our very first one that we had. First come, first served. This is the same set of processes coming in at the same time with the same burst time. Originally, process 1 just got in and kept going and kept going and kept going. With round robin, what we have is process 1 still coming in at the start, but after 4, it gets chucked out. So it's not finished. It's down to 20 at this point, and the operating system says, nope, you've had your time for something else to get a go. So process 3 gets a go. But actually, process 2 gets a go with a burst time of 3. But process 2 only needs that 3, which is less than our 4, so it executes and finishes at 7. And is done. We then go into the next one on our list, process 3. It also only needs 3, starts at 7, finishes at 10, and then is done. At which point we're down to process 20, which starts up again at time 10. So another question. Why is the graph showing these time marks at 14, 18, 22, 26, and so on? Anybody? The operating system has a time quantum of 4. So every 4 units, it's going to check to see whether there's another process that needs brought in. Now, as it happens in this example, there isn't, but the operating system's still checking. So at 10, process 1 gets 4. And then at 14, well, there's nothing there, so it gets another 4, and then another 4, and so on. But if another process had come in, process 1 would be stopped, and something else would be popped in. So we have to make decisions every 4 units here. We also had to make decisions that it was 4. So depending on the processor speed, depending on the type of operating system, depending on the type of work you're expecting it to do, depending on the type of processes, depending on the number of users, all of that stuff will be taken into account to decide what the appropriate time quantum is. Maybe between 10 and 100 milliseconds. That's assuming that it takes less than 10 microseconds to switch contexts. That may or may not be the case depending on the CPU. And of course, CPUs get faster all the time. because that has a large effect on what can happen. If we have a quantum here of 12 with a process time of 10, well, there are no context switches involved. It gets completed. We half that to 6. Nope, there's a context switch and we have to swap at some point. A quantum of 1 gives us lots of context switches. So it's about finding that balance. And I've said it before, and I'll probably say it again another 20 times before we're done, there is no correct answer. But we'll do our best to reach the best answer that we can get. One of the ways that we can do that is by looking at the average time that it would take and trying to ensure that the work that goes through, we minimize the amount of context switches. And the rule of thumb that we have here is the time quantum should accommodate 4 out of 5 of the CPU bursts. It is a rule of thumb, it's a reasonable one. So you'll look at the type of work that goes through the operating system, figure out what the bursts are, and make sure that 4 out of 5 of them are within the time quantum that you've set. But it's very much a lick your fingers, stick it in the air. Yeah, it's a bit more complicated than that, but so I said before that these are approaches, but actually one approach might not fit all. Some operating systems don't just have one queue, they have lots of queues. They might have queues for things that need to happen. So on my system, I might have a queue that is watching for that mouse pointer and making sure that when I move the mouse, the pointer moves. Because I want to see that happening. I don't want a delay. On the other hand, in the background, I've got OneDrive synchronizing my files with my online OneDrive and my local OneDrive storage. I don't care how long that takes. I probably do care if it interrupts me doing my work. And probably everybody on this meeting has heard me complain about my computer doing stuff in the background, whether it's synchronizing OneDrive or downloading the latest update or whatever. But what it's done is it's compromised the interactive stuff. So you might have different queues for things that can happen interactively and things that can happen in the background, which we call batch. And you might put those processes into those queues to begin with and say, okay, this thing has to happen interactively, this thing can happen wherever, we'll do it in batch. And you also might decide, in fact, you probably would decide, to give different algorithms to those different queues. So the ones in the foreground, the interactive ones, give a certain amount of CPU time to each process, so that everything that you're working on, each of the interactive things gets a wee bit, so that you can see that things are happening. So that I can see that PowerPoint's updating, and I can see that Teams is updating, and I can see when I scroll on the slide that it updates. But I'm not continually checking the stuff in the background. My OneDrive, my downloads for updates, my antivirus. So actually they can just get run using a different algorithm as well. They can just get run using first come, first served. Whatever asks for it first, yeah, do it. They're all in the background, it doesn't really matter when they happen. So just do first come, first served. So we've got two queues running different approaches. There's a possibility that if there's so much happening in the interactive queue, nothing ever happens in the batch queue. So again, you might want different approaches. You might say, okay, well, if something's gone into the batch queue to work in the background, but it's been sitting there longer than a certain time, stick it into the interactive queue so that it gets some CPU time eventually. And again, we can use maybe aging or something for that to decide when that happens. Or we could split our resources and say, okay, well, if we have jobs in both the interactive and the batch queues, let's split our CPU time. We want interactive to happen, so we'll give that most of it. In this case, we've chosen 80%, and the background stuff gets 20%. Again, different approaches, none of them are the one, they are approaches. Some operating systems take that idea and go further, so that you don't just have two queues, you can have lots of queues. So a system process queue gets the highest priority. Me moving the mouse, me getting a background network packet, me sending out a background network packet so that you can see this happening. Interactive processes. So if I point to interactive processes here, I can actually see on my screen that it works faster on the screen that I'm doing it on than it does on the screen that you're seeing it on. I can see in real time the part where I've drawn it, updating, and then I can see it slowly appear on the Teams display. So system processes at the top, then interactive editing, then the batch ones, you know, the things that would go in the background and we don't care when they take. And of course, as it should be, any student process takes the lowest priority of all. And as we said, for foreground and background queues, we can decide to move processes between queues. But again, that takes more thought, it takes more decision making. We have to decide what the queues are, what goes into them, what process we're going to use to schedule, what process we're going to use to move them between those queues, and all the stuff that we've talked about before. Sometimes you might want to upgrade them, sometimes you might want to downgrade them. You've set something up as an interactive process and it's not doing anything. Stick it in the background. Stop it taking time. So you might want to use what is actually going on as part of that decision-making process. So here we've got 3 queues. So processes come in with a quantum of 8. We have worked out that 80% of CPU bursts take 8 or less. So say, okay, we'll have a queue that works on those. But then we'll have a queue that gets a longer time frame, 16 say. So if it comes in to the top queue and it's not one of the 80% that executes within those 8, so execute and exit within 1 burst, then we'll put it into our next queue. And because we already know that it takes longer, this queue actually gives longer for the CPU burst. It takes 16. That will probably take another 19% of our processes. So they'll exit at that point. And the remaining 1%, this is an example, don't quote me on it, the remaining 1% will then go into a first come, first serve queue, one where we've said, okay, these are taking a long time, so we'll give them to, we'll take them in order. So multiple queues with multiple strategies, and multiple reasons for moving them between those queues. So it just depends what you want to happen. That's the background. That's how things can work. The next part of the lecture is about examples. So I've got examples of Linux, Windows, and an operating system called Solaris. I'm not going to go into great detail on them, in part because you're going to have to go back, try and understand what I've been talking about up till now, and then see how that has worked in the application. So the reason I'm going over these quite quickly is because you need to go back and understand the approaches and how they work before you look at them in real life. So the first one we'll look at is Linux, and I'm not going to read out the slide to you, but of course you won't be surprised to know that it's a preemptive operating system because there's interaction involved, with a couple of priority ranges and an option to be nice when you set up your process and leave it to go. It uses something called the completely fair scheduler. So it tries to be fair in terms of the priorities that each process has. So it has multiple scheduling classes, but also multiple priorities, and it tries to work out between those how much time to give them. It also asks for input from the user for this. So for example, you can on a Linux or Unix system start up a process. So say you were running a 3D render. Instead of just starting that process at the command line, render fred.blob or archive my files /star, things that you know will take a long time, you can prefix them with the word nice. And nice allows you to set a nice priority. You're basically saying to the operating system, I'm starting this process, I'd like it to run obviously, but I'm not in any rush. So do it, get back to me when it's done. So you can say something like nice -19, nice 19, which is at this end of the priority scale. The lowest number has the highest priority. So you can say nice 19 render. And the operating system will go, thanks very much. I'll give you CPU time when I can, but I'll let the other things run first. And that gives a decent performance. Windows also is preemptive, also uses priorities, and the dispatcher is within the scheduler, so they don't have two separate things happening. It's the same bit. Priority based, and there's 32 different priorities. And as I said earlier, some things take priority. In this case, for Windows, it's memory management. So moving stuff about in memory takes the priority over everything else. We've got 32 priorities, and actually there's 32 queues. So there's one for each of those priorities. And we can actually set those up when we are programming. So there's stuff in there when we can say, do this, do whatever. So there's a whole bunch of priorities and a whole bunch of options for whether things are really important or not important at all. The other one we're looking at is something called Solaris, which is a Unix-based operating system. In fact, the reason we've chosen this is it actually uses a priority-based system, and it's got 6 different classes. So you can be running something that's time sharing, so interactive stuff. Sorry, time sharing, but no interaction required. That's different from a time sharing where interactivity is required, which is different for things that have to happen in real time. In other words, the response must be immediate. We have system classes, we have fair sharing, so the nice thing again, and we have fixed priorities. So it will have different time quantums for each of those priorities, depending what they are and what's required. And it has, as you can see here, lots of different priorities from lowest to highest, and of course the highest priorities will be scheduled first, things like interrupts, then real time, and all the way through to interactive threads. So it's quite a complicated setup. It looks at the class that the process is in, it looks at its priority, it looks at how long it's had, all that kind of stuff, and uses analysis of what has happened in the past and what it expects to happen in the future in order to try and figure out how it's going to schedule them. And of course, we can do that when we are creating our operating system. So we don't just go into creating an operating system and go, oh, I am Windows, I will use a priority-based preemptive scheduling mode. Or I am Linux and I will use a preemptive priority with 2 priority ranges. You try and figure out what the operating system is, what it will be required to do, and then you try and work out the best approach. And oddly enough, one of the things that we can do is take the data that we have. So for example, on this system that I have here, I could record what's going on. I could record the CPU burst. I mean, I've been talking blithely about, oh, CPU bursts, time quantum should be enough to accommodate 80% of the CPU bursts. Well, how do you know how long a CPU burst is? You have to do some analysis at some point. So we can look at a working operating system. We can look at workloads. As I said, we'll develop different operating systems for different types of workload, depending whether they're interactive or batch or whatever. And then we can look at example workloads for each of those. So here's multiple processes with multiple burst times, and start feeding those into the different options that we have. We can feed them into a first come, first served, or a non-preemptive, shortest job first, or round robin, and we can see what happens. Take those example, but taken from real life processes with the burst times, stick them in and calculate according to our criteria how well they do. Calculate the average waiting time. We can see here that non-preemptive, shortest job first, another error on the slide, is 13 milliseconds. But waiting for other criteria might not fare so well. So we can actually work out the stuff and use those to decide. And we can actually start to create models from that. We can look at all the things that we want to maximize, all the things that we want to minimize, the criteria that we've spoken about before. And we can either take real examples, so we can record an operating system, or we can create sample data. And that's usually, well, on average, it will take its usual for. And we can plug those into another equation. And it's something called Little's formula. So we can take the stuff that we have examined, we can figure out the average queue length and the waiting time in the queue and so on, put them into Little's formula to ensure that work progresses through the system in the time that we require. Bottom line, as it says there, we don't want processes piling up. We want to get through the work. So in essence, the processes leaving should be the same as the processes arriving. If the processes leaving are lower than the processes arriving, our computer will slow down. The work won't get done. And you've probably all experienced that even on your own systems, where you've had lots of things running and the system simply can't get through them all. So processes leaving being the same as processes arriving is about the best that we'll do. But it does have knock-on effects on how long you'll have to wait. So if we can get through more work and chuck it out, then clearly processes won't have to wait as long. But then we won't be utilising our CPU to its highest extent. So again, it's about finding this balance, about trying to get the best possible use out of our systems. So once we've taken all that into account, once we've recorded all our data, once we've worked out algorithmic models, we can then simulate it. We can simulate those examples, stick them into first come, first served, stick them into shortest job first, and start evaluating which one does best. Or should we have multiple queues? And if we do have multiple queues, what should the time quantum be? And all this kind of stuff. So that we can start modeling to see what gives us the best throughput. And of course, anybody who's writing an operating system is doing that all the time to try and get the best possible performance for their operating system. And they do that because if you just guess, if you do as I suggested earlier, just stick your finger in the air and hope for the best and distribute your operating system, well, that costs quite a lot. And if it doesn't work as you expect, well, that's going to cost even more. What you can do, though, is use the idea that schedulers, dispatchers, they're bits of a program. They're written like anything else. There's nothing stopping you distributing an operating system with different types of scheduler. And you can choose the scheduler that you want. There's nothing that stops you saying, well, let's write a new scheduler and do it differently for the kind of jobs that we have. Big IBM mainframes do that all the time. Third parties, companies that aren't IBM, will actually write schedulers that you can stick into your system Z to cope with different job mixes, depending on the kind of industry that you're in. Bottom line, there are lots of different approaches. None of them is correct, but all of them have their benefits and their drawbacks, and it's up to whoever's designing the operating system to understand those and implement the ones that are most appropriate for their operating system. Anybody, any questions? I'm not seeing anything in... Oh, no, there's one in the chat. Everything's okay. I'm not seeing anything in the chat. I'm not seeing anybody with their hand up. So I'm assuming that you're all right with this. As I say, it will take you a little time to go back and just make sure that you understand those diagrams. And you really should make sure you understand the diagrams. If you do the chapter test, you'll see that they appear and you'll have to fill things in. So there's a fair chance that you'll be assessed on them too. If there's no questions, remember today is an opportunity to come on campus. So we'll start a lab at 2 o'clock. So once I'm finished here, I'm going to jump in my car or jump in the train. I'm not quite sure yet. And we have an entirely optional on-campus lab. So if you want to come, you're very welcome. If you don't want to come, that's absolutely fine too. But I'll be on campus this afternoon if anybody wants to be there. So other than that, let me stop the recording